into it without any further ado. So area problem. We were going to talk about how to calculate areas under the curve. So, of course, yes, there are a lot of pages to the notes, but there's not that many examples. It's a lot of prelim, setting up, how are we doing the calculations to find these areas. Now, like I said, it's a combination really of all of this summation stuff along with limits. So first off, we're going to use our concept of a limit by our formulas back in chapter 12. If just a little throwback, that is a geometric sequence, that a1r to the n minus 1. We have looked at that formula. It was on your formula sheet from last chapter. Like I said, we're combining all of this stuff together. And for the record, these formulas on the board are obviously in your notes, clearly. I will also provide you these formulas on the test, just for the record. But you're going to have to use them. So these are some of the different summation formulas we're going to see today. I'm going to be honest, the cube one's no bueno. That's kind of a pain. The biggest ones mostly we're going to go through is squared today. I debated on even throwing cubed on there, but I wanted to put it on just in case. You never know if you might see that in a bonus level type question or something like that. Okay, so we're going to start simple, working our way up to this area problem. Clearly this has nothing to do with area yet, but like I said, we're combining the sum along with the limit today. So this is nice and easy. You can see in example 1, I'm going to click it ahead again. It's this I formula. So in the old days, aka last chapter, I would be asking you to find me the sum of the first 200 terms. I'm not going to add 200 numbers. Let's just get serious about that. I don't even want to necessarily do math 0. That's a little more time consuming. Then I can just do this formula. So I'm going to use the second formula. Our n is 200. Gentlemen, please be quiet in the back. I'm going to replace both n's with 200 and just crank it out. So 200. I did click it. So 200, we got it. Times, of course, 200 plus 1. I mean, I know you'd just put 2 on 1. I'm just setting up your formula. And of course, over 2. All you have to do is calculate that out. You get 20,100. Now, is that quicker than doing math 0? I don't know. I guess it depends on how quickly you type. Personally, I don't think that's too hard of a problem or too slow of a problem. But just to kind of set it up, because like I said, we're going to be using these formulas today. All right, page 1 done. There we go, everybody. Crushing it. Okay, find the limits. Here we go. We're combining the limit with the sum. So here's where it's going to start to get dicey. So first off, we've got the sum. There's the I in there. You can see the I over n. I want to try to use one of those formulas down there, combined with the limit to infinity. Now, we did limits at infinity yesterday. If I can get this to a rational, I'm pretty sure I can, I see those fractions, a rational function, I can think about that horizontal asymptote. I can look at those degrees and decide whether the top's smaller and it's 0 or it's going to be lead coefficients. But we got to like boil it down to that rational expression. So here we go. First up, I'm trying to figure out how to space it so I can fit everything on the screen. First up, I'd write small. Now, we need to simplify this. AKA, we need to FOIL it out. We need to distribute the 1 over n through. Hard? No. Time consuming? Definitely. So I'm going to start by FOILing this. We're just going to FOIL it 1 times 1. Then you'd have one of these fractions and another one of those fractions. So your middle term, you have 2 of them. And then you're going to have I squared over n squared. And we still have times 1 over n. Okay, so of course I'm going to go ahead and distribute the 1 over n through, because I want a single, nice, pretty expression here. So not difficult, but just very, very time consuming. So I'm distributing 1 over n through. 1 times 1 over n, got it. I'm going to have my 2i n squared. And then I'm going to have I squared times 1, I squared, and then n squared n cubed. So that is just the setup, my friends. Now, again, let's click it back a couple slides here. I want to try to use one or more, we'll just see these formulas that have I squared, hopefully not I cubed, because that one's kind of scary on it. So I want to try to simplify this and get it down to just I. Now, like I said today, easy but a lot of work, because we're combining our skills or our knowledge about summations along with limits at the end. So our summation knowledge, we have these three fractions. We can break it up, and I can do part of our chapter 12 summation knowledge, the sum of each one of these expressions individually. So that's my next play. So I'm just separating it, 1 over n plus the sum, and I really like drawing these e's. Sarcasm. And another one. I squared n cubed. All right, I'm going to scroll it up just so I don't end up at the way bottom here. Now, still going. So we've got the three sums, and like I said, we're trying to just get those expressions to have I in them, so I can use those formulas on the board or in your notes. So here comes the fun part. So what I'm going to do, this one's super easy. Some of our summation knowledge from the last chapter. I'm going to pull out that 1 over n. So in the front, I equals 1, n, and then you would have 1 left. So it's like you're factoring it out. I'm going to do the sum of this constant term 1, which is going to be super duper easy, and you can times by 1 over n at the end. Got it, okay? Another one. I'm going to color code. Let's do the middle in blue. Now again, I'm trying to get it to just have like I here. So I'm going to factor out of it the 2 over n squared. And you'll see why here. Oh boy, I drew that one messy. And then I've got the I. And I'm going to do the third one in black. And I'm going to factor out, because I want just the I, 1 over n cubed. That's a very sloppy one. So we're trying to just have I, the sum of the I expressions, because now, you can look on the board or of course on your notes, I'm going to replace those with these appropriate formulas here. And we'll have all variable n. Let me scroll it back up, everybody. Okay, so the first one is the first formula up there on the board. Number 1, the light blue one, is you have your constant term. So that one's super easy. Just the constant term times n on the top. Got it. Okay, so I'm going to keep my 1 over n. I'm going to put my dramatic times symbol in, because why not? And the summation of this constant term is just n times 1. n times 1, n. Yeah, I know those cross off, and I'll do it in a minute, okay? Middle, blue. I'm going to keep my 2 over n squared. Now, summation of just I. That's the purple one up here on the board. I'm going to replace the I with n plus 1 over 2. N plus 1 over 2. And we will simplify and multiply and do all the stuff in a minute. Okay, third one. I'm going to replace that summation of I squared, that's the red one up here, n plus 1, 2n plus 1. And again, I'm going to give you these formulas. You don't have to have those memorized for the record. Okay, now we have it all in terms of n, which is super great. I'm going to hit extend page here, and we're going to simplify all of this good stuff to the very best that we can. Now, nice thing is the n's cancel here. 1. I'm going to work on this blue stuff a little bit. I can get rid of the 2's, and I can reduce this n squared down. So I'm going to have just n plus 1 on the top and an n on the bottom. I'm going to try to get the black going here. I'm going to try to simplify. I can't do a whole lot with it, but a little bit of reducing. I could reduce the n and n cubed. I'm going to make this a squared. So on the top, I'm not going to write the 1. Let's go ahead, though, because I do want to try to combine some like terms. I'm going to FOIL this out. So I'm going to have 2n squared plus n plus 2n. Let's combine it to 3. And 1 times 1. And I've got n squared and 6 on the bottom, 6n squared. Okay, our goal now, our fun-filled goal, is I want to combine that into one expression. Because remember, the goal is we're combining our summation knowledge with a limit. Because remember, limit to infinity is the goal if you read the directions, which are right at the top of my screen here. Okay, so in order to do that, I want to make it that rational function so I can look at those exponents and get my final answer super easy. This is just an algebra nightmare. If we're going to add these up, we need a common denominator. Okay, so 1, I'm going to think of that as 6n squared over 6n squared. I mean, that's pretty easy. That's 1. Okay. This guy, the blue, I'm going to have to throw a 6 on it and another n. and that will make 6n squared. So I've got my common denominator, and we can put the like terms together, see what we can make happen here. So the top, 6n squared times 1, I got it. I'm going to take 6n through here, another 6n squared, and a 6n. And then I've got all this stuff on the black. And this is making my hands start to hurt. Over 6n squared. Let me scroll it up again. Combine your like terms. So 6, I'm doing the n squareds. 6, 12, plus 2 more, I've got 14. 6n, 3n. Okay. We're actually almost done, thank God, right? So I can scroll it up for the directions here. Find the limit of the sum. Well, we cleaned up the sum and put it in that nice, pretty function. Most of you can probably just write down your limit now. I'm going to make it nice and pretty as we're approaching infinity at once. And we have our nice rational function we did all that algebraic work on. So we know it's the horizontal asymptote from yesterday. When the degrees are the same, what's your answer? 14 over 6, the lead coefficients. And of course, good mathematicians that we are, we're going to reduce that to 7 over. Wasn't that fun?
No.
I love it. Love it. Now, you might be questioning, why are we doing this? Why are we doing this? Why are we torturing you with this? Because it's coming at us. Remember, the title of this section is the area problem. We are going to be trying to find area under the curve. That is a huge calculus topic. When you get in calculus, it's going to be a whole lot of this, okay? Now, in order to do that, which is coming up here, we have to be able to do the sum and limit combined. That's why we started you off easy. That was easy. And we're practicing. Okay, we've seen limits are needed to compute the slope of a tangent line or instantaneous rate of change. We did that back in 13.3. Here we're going to talk about, of course, finding the area under the curve, the area problem. The area problems, that's the problem in calculus, find the area of the region that lies under the curve. Now, area is easy if you have straight sides. You did a lot of, geometry. Length times width, did a triangle, half base height, all that sort of good stuff. So in trying to solve the area problem, we've got to ask ourselves, what's the meaning of the word area? It's easy on straight line figures. We all pass geometry, we know that. But when we have curved sides, here it comes. We're going to have to do the area of the region, of course. It's going to be hard to give an exact definition to this. We're going to do a little limits on it and summation together here. So recall in defining a tangent, approximate the slope by the secant line, and we did limits. Limits, summation. That's what we're putting together here today when we get to it. So we're going to approximate the region by rectangles. So you're going to see that same picture come back up. I'm going to make rectangles as best I can out of it, and we're going to try to find the limit. So here we go. Oh, this is going to be good for my art skills, kids. Not really. Okay, so use rectangles to estimate the area under the parabola. We all know what a parabola looks like. Mine's in red. From 0 to 1. So we're only looking at this specific area or region of it. So first it says divide it into 4 strips. S1, S2, S3, S4. Here's, okay, my artistic skills. I'm going to try to split it in the middle and then each half. Oh, God. So this would be my S1, S2, S3, S4. So we're trying to split it into 4 lovely rectangles. Now, we can do area of a rectangle. What's the formula for area of a rectangle? Length times width. So that's what I'm going to try to do, is I'm going to calculate the area of each of those 4 rectangles with some length times width and add them together. Now, let's start with the easy thing. They all have the same length. What's the length of each rectangle?
1/4.
Okay, so we just equally divided by 4. We just picked 4. Now, does it have to be 4 rectangles? No, you could have done 12, you could have done 6, whatever. We're just trying to start with something easy. So we want to try to calculate the area of each of these rectangles. Each of them, of course, has a width of 1/4. From a half to 3/4, it's a 1/4. 3/4 to 1, it's a 1/4. What we need, of course, is height, or we need a y coordinate up there. Now remember our function, we're doing y equals x squared. Next slide here. So we can approximate each strip of the rectangle whose base is the same, of course, as the height. In other words, the heights of the rectangles are the values f of x equals x squared at the right endpoints. So let me go back to my picture here. So if I want this endpoint, the y coordinate of it, y, I'm going to use this guy. I'm going to put 1/4 in here. What's 1/4 squared? 1/16. So that would be your y coordinate. And I'm just going to keep going here. What's, of course, if we put a half in, what's a half squared? What's 3/4 squared? 9/16. 1 squared, 1. We can see it up there. So when I go to do my area of each rectangle, which I'm going to put on the next slide, I just can't fit it all in here. I'm going to do my width, 1/4 times the height. 1/4 times the height. 1/4 times the height. So when I go to find the area, this is what they're asking you for. When I go to find the area of that first one, so the width was the 1/4, and of course the height was the 1/16. And I calculated that out earlier. Now I'm going to do the second rectangle. Let me go back. So my second rectangle here, the width is still 1/4, and of course the height 1/4. What's 1/4 times 1/4? 1/16. When I do my third one, back to the picture. So of course my third one here, the width is still 1/4, the height was 9/16. So 1/4 times 9/16. You're going to get 9/64. And the last rectangle, so of course the width 1/4, height 1, that's easy, 1/4 times 1. We got that one right. Okay, so our approximation of the area is of course the sum of all those rectangles. So we would add, I'm not going to write all the fractions out, we're just going to add these together, of course, which I did earlier. And you end up with the lovely 15/32. Now, here's a question for you. How accurate do you think that is?
Not very.
I question it, right? Would it be more accurate if I had more rectangles?
Good.
Yes, if I split it into smaller and smaller strips. So that's where our limit's going to come into play to infinity. We want to try to estimate this area under the curve as exact as we can. So of course, if we use larger number of strips, it will be more accurate. So I'm going to just put increase here quick to answer that. And let's get to it. Okay. See, we're cruising along. We're cruising, Kale. We're cruising. Okay. Cruising. So not a lot on this, just some more information and those formulas again in front of you, so they're there, okay? Now, again, here you can see they divided it into more strips. More strips the better, of course. So one of the things that's important, because we're going to be doing base times height, or width times height, however you want to look at it. So one of the things we're going to calculate, of course, because we had 0 to 1 on our last problem, you might have a different interval. So of course you're going to have to look at this guy. So the change in x, that's what that little triangle symbol means, the change in x. You're going to subtract your endpoints and divide by how many rectangles you're going to make in this situation. Now we're trying to do close to infinite rectangles, so we get it as close to an exact answer, more accurate than just if I split it into 4. Okay? So you're going to subtract, that's going to give you the width of each rectangle. So you're going to subtract your interval value, so it might be from like 2 to 7, so 5 when you subtract it, and divide by n, your number of strips. Okay, this looks crazy, I know. This is all the same that's on the board. I just put them here so they're in front of you again. So the formulas, of course, at the bottom are the same. We're going to use those, of course, today. Here is the big one that we're going to work on. So, to find the area, of course, we're doing width times height, base times height, however you want to think about it, okay? Now, it's going to be the limit, because we want to get close to infinity, as many rectangles as we can fit in there, and we want to add them all together. So that's where I said it's a combo day of summation plus limits. Now I hate that this, to me the order's kind of weird. I like this one first. To me that's the width. You know, when I teach geometry, I always teach, you know, base times height for the width. I like that one first, but it doesn't matter. And this one's the height. And double check, I don't think I caught it before I ran yours off. I think my fraction bar got carried away here. Is this A on the fraction bar? It should not be. A is separate. I got carried away with my fraction bar. And I feel like, I haven't decided, but I might give you this formula too for your test.
You weren't going to give it to us?
No, it's length times width.
That does not say L times 8. Or
I love it. I love it.
it.
All right, are we ready?
But
Are we ready?
it doesn't have
We're ready. Okay, I feel ready. Find the area of the region bounded by the curve. Y equals x squared, starting you off with nice and simple, and of course between 0 and 1. So, excuse me. All right, so I'm gonna start with the width first because that's what I like. That's how I roll. So the width of it. I'm gonna subtract our interval. I'm gonna do 1 minus 0. I'm looking at these x values. You can do that in your head. And we're gonna divide that by n amount of strips. Now the first time we did it, I did 4, because I could fit 4 in there kind of nice with my drawing skills. Today we're going n. We want to get close to infinity, as many strips as we can possibly fit. 1 minus 0, you know, got it. Okay, then we need, of course, an expression for our height. Did I say right small? I probably should. Okay, so height. So back to this formula. So it is of course, our A value, what we just calculated. These are the same, but notice you have the I on it. So let's go back to this one. So I'm going to take a look at it, of course, and we're looking, our first starting value is at 0, plus our 1 over n, and it has the I value on it. That's an I, sloppy I. Now, I don't need the 0 plus. I mean, come on now, since we're starting at 0, that's where the 0's from. I'm going to get rid of that and just put it F of, I'm going to put I over n. So that is what you're putting into the function. I'm still going on the height here, still going, my friends, because I'm going to go ahead now and I'm going to put that into F. So I'm going to replace the x with I over n. I'm going to have to square that. So I'm putting this into the F function. I'm evaluating the function. So I'm just going to go I squared over n squared. Okay. So you've got the width, you've got the height, we're ready to go. Now remember, combo. We're looking at the limit to infinity. We want to get as accurate as we can. Infinite rectangles, as many as we could fit in there. And of course, we want to add them together. So it's the sum. Well, I'm going to start with the sum part first and do the limit at the end. So let's area equals sum. And we're going to do width times height. So 1 over n. There's my width, height, I squared over n squared. So it is just like that last example problem we did. So this just irritates me. I'm going to make it n cubed on the bottom. Oh man, I drew that one bad. Don't judge my drawing skills. Now again, I want to be using, of course, the formulas on the board over here. So I'm already zeroed in on this red one, the I squared formula. So just like the last problem, our knowledge of summations, I'm going to, dramatic there, I'm going to factor 1 over n cubed out. I'm getting worse at drawing these as the day goes. And then I've got my I squared. Now I'm going to use my number 3 red formula here. I'm going to replace that I squared with n plus 1, 2n plus 1. You can see it all over there. So this limit, we're going to replace it with the red one, n plus 1, 2n plus 1, and of course we are over 6. So we're getting there, believe it or not. So the goal is we want to clean that up. I want to simplify it. It will be a rational expression. We're going to do the limit to infinity. We want an infinite amount of rectangles under there to get as close as we can get it. And then we can easily look at those exponents and get an answer. We are, believe it or not, on the home stretch. Let's clean this up though. I'm going to reduce the n and make this a squared. And I'm going to go ahead and FOIL out the top. So I'm going to have 2n squared, 2n squared, I'm going to have plus an n, plus 2n, plus 3n, plus 1. And left in the denominator, I have n squared and 6. I'm just going to flip-flop them and make it 6n squared. Now, some of you can probably slap down the final answer right now. I got to be fancy about it. We are now going to do the limit of this expression. We want to get as close to the infinite amount of rectangles you can make. I know you know your exponent properties from yesterday. You've already finally, I'm guessing, have the answer of 1/3. And I'm going to put unit squared because I feel like I should have a label on an area. It just bothers me. Okay, so quick question for you. Hang on, Elliot. Quick question. Remember, whoop, too far. This is kind of the same problem we looked at, that y equals x squared, where I split it into 4 rectangles versus infinite. Is 15, 30 seconds, if you punch that in your calculator, what's 15 over 32? Is that, how close is that to 1/3?
It's kind of pretty close. Well, it's like 1/2.
It's not very close, is it? It's not very close. My lousy 4 rectangle approximation didn't get me very close to 1/3. That is why, if you're like, why can't we just split it in 4 and do it in the atom? This is why we have to go through the sum and the limit. It's painful, I know. Elliot, what do you got for me?
I just wanted to ask, how do you go about factoring the n terms out of the expression?
Because you're just multiplying. That's part of your summation rules back from chapter 12. If you remember all of those, you look back in that chapter, that's where all of that comes from. All those summation properties. Hey, let's do another. We've got time. Yeah, we do. Yeah, we do. Let's do
C, so we don't have to do B.
All right, I can get on board with that. Let's do C. I don't think we need both. I think we can go to C. Let's do a little different interval too. Okay, so same thing, bless you. First I'm going to do the width. I don't know why I always like to start with the width versus the height. That's dumb, but I do. So the width, I'm just going to subtract our interval. I'm not writing 5 minus 2. Just do it. What's 5 minus 2? 3.
4.
And again, we're going to divide it by however many rectangles we could fit in there. That's what n represents. Height is a little dicier. Height. Because that's where you're evaluating your function, so don't forget the f on it. We're going to put this in our function. Now, our starting value of our interval, we're starting at 2. And we're going to add to it, of course, our width here, this 3 over n with the I. Now, we need to actually evaluate that function. So I'm going to put this crazy looking expression in here for x. So I'm going to have 3 times this whole bunch of stuff, 3i over n, and then don't forget minus 6. And actually, that's going to come out kind of nice, because what happens to the 6's? They'll cancel, so we don't even need to bother writing them. But I'm going to do 3 times 3 there in the middle. What's 3 times 3? 9. So we're going to have 9i over n. Okay, so we've got our width, we've got our height, we're ready to go. So we're going to start with the summation, because we want to add up all the rectangles. I'm going to try to draw these a little better today. No promises. And of course, my width times the height. Now, yes, I know you could just multiply that together and make it 27i over n squared. I'm well aware. All right, 27i over n squared. Now, we want to use our formulas here. We want to get them, of course, all in n, all in the variable. So I'm looking at the I one, which is not so bad. Thank God it's not IQ'd or anything. But before I do that, I'm going to kind of factor out some of this using our summation properties from the previous chapter. I'm going to take the 27 and n squared. You don't need the, oh man, I drew that one bad. So because 27 over n squared is your constant we're multiplying. Now I'm going to use my formula here for this. I'm trying to decide if I can fit it in here. I'm going to try. So I'm just taking a look. I, of course, it's the purple one, n plus 1 over 2. So We got the same variable n in here. We can clean this up. This isn't going to be that bad, I don't think, as far as distributing, etc. And then we'll do our limit to infinity, and we'll look at the exponents. So let's, 27 over 2 doesn't reduce. That's kind of bogus. I can at least reduce, I guess, the n and n squared down. That'll make it a little bit nicer. So let's take 27 through the top. So 27n plus 27, and then 2n. Now, some of you can give an answer right now. I'm pretty sure. Pretty sure. Technically, we have to recognize we're doing the limit of infinite rectangles of this expression. Bless you. And now it is a rational expression. Clearly, our exponents are the same, so it's the lead coefficients. Final answer. Got it. And because it is an area answer, we should throw a label on unit squared. Now, let's think about this. This is so much fun. I love it. Okay.